Hello, good morning and good afternoon to everyone tuning in for this month's Geotherum session. My name is Jackson Grimes, and thank you for joining us. Earlier this week, we celebrated World Geothermal Energy Day, and today we will be learning about research going on in a part of the world people don't usually associate with geothermal, Texas, which I find really exciting because it shows the extent of geothermal's growth and how more and more folks are getting involved in this research and really building the sector. So specifically, we're going to be learning from the Geothermal Working Group at the Bureau of Economic Geology. The Bureau is the State Geological Survey of Texas and the oldest research unit of the University of Texas at Austin. The University of Texas has several classes focused on geothermal energy. Two of our professors are here with us today, actually, and we even have a course on geothermal law. The university is located in Austin, which is the capital of Texas, and we have 19 individual laboratories at the Bureau, which host researchers from around the world who investigate everything from nanoparticles to shale porosity and permeability to hydrogen and most recently geothermal. The Bureau is over 200 scientists, engineers, economists, and grad students who represent 27 countries, and we're always looking to add more dedicated and talented investigators to our team. So if you would like to learn more, you can find out about the Bureau online or reach out to me personally on LinkedIn. So first, I would like to introduce one of the professors of geothermal and our first researcher, Dr. Ken Wijan. He is the Associate Director of the Environmental Division here at the Bureau, as well as a retired Major General of the United States Air Force, which has given him a unique perspective on the potential for geothermal. He is also the principal investigator for the Bureau's newly formed Hot Rock Geothermal Research Group, which is an industry-funded research consortium investigating and filling science and technology gaps needed to develop the Geothermal Anywhere, or EGS and AGS concept. I also want to mention his research into planetary geology, which is super fascinating, and in particular, some studies about geothermal on moons and other planets. But today we're talking about Texas. So Ken, I'll let you take it over from here.
Okay, thank you, Jackson. It's a pleasure and an honor to be able to speak with you today. We've got multiple presentations on Texas. We're also the Geologic Survey of Texas, but we do work around the world, and we're very interested in developing more partnerships in Central and South America in this booming area. So I'm going to share my screen just a second here. Okay. Looks like that's working now. So I'm going to give you a brief overview of Texas and the booming geothermal research and development that's going on here. But obviously, it applies everywhere in the world. We're just a good case study. But as you look at Central South America, Asia, the whole world has a tremendous amount of undeveloped geothermal resource, both the conventional kind that I'll mention and the emerging new paradigm of geothermal anywhere. So with that, I've been a geothermal geophysicist since the 1990s. That's my PhD subject. But right now is far and away the most interesting time, most exciting time I've seen in my whole career in geothermal. And I'll explain a little bit about why in a minute. But up till the last few years, geothermal development has been really limited, both on the financial side, but also particularly on the geographic side. And that's because all the existing geothermal is hydrothermal. So it relies on finding a natural hot water or steam system in the ground and developing that to produce electricity. That only occurs really where you have a tectonically active area. So subduction zones, plate collision zones, volcanoes, hot spots, that kind of thing, which is roughly but not completely illustrated in this picture here. But you get the idea. So much of the world has not really been feasible for geothermal development since the beginning of the industry until now. And that is where geothermal anywhere comes in and potentially opens up the entire surface of the Earth to geothermal development. But even on the conventional side, it's still estimated just in the US alone, where it's fairly well explored, that there's 3 times the potential in hydrothermal systems compared to what's already been discovered. And the same multiplier will only be larger in other parts of the world. So if you look at the United States in general, the continental US, we have a distribution like this. And if it may not be visible, but there's yellow dots where there's known geothermal systems. They're all from the Rocky Mountains west. And again, that correlates to the tectonic activity. Lots on the west coast and in the what's called the Basin Range, which is an extensional system. But I look at this map as a map of potential. So the hotter looking areas are where the resource is really developable right now with current or near current technology. But as the technology advances, even the cooler areas, for instance, in the eastern US, will become economically viable for geothermal energy generation development. They're already viable for direct use, and we might get into that in the questions and answer section. But the point being that geothermal anywhere is focused on developing the regions of the world that haven't been open to development up till now. And in Texas, it's perhaps the hottest development area, pun intended, in the United States for new geothermal projects. We do have hot zones. Let me change my pointer laser. There we go. So we do have hot areas here, not quite as hot as the Western US, but still developable now, and there are multiple projects brewing. The government has issued geothermal leases in the past year, one out here in far west Texas, one here in South Texas below Houston. And there's multiple other private or public projects that are starting up, some of which have not been announced publicly, some of which have. So if you look at Central and South America, you see similar patterns. You see, in this case, this is a gradient map on the left and I believe it's a heat flow map on the right, but the general idea doesn't matter if you're using gradients or heat flow. You're showing the relative hotness of the upper few kilometers of the crust, which again translates into the easiest versus the hardest areas to develop. And obviously where you've got tectonic activity, there's already developed systems, but there is a lot more potential there and in Central America also related to this. But, that part of the words got covered up. Hidden in these maps, what you can't tell necessarily is that there's large areas of these maps are really not explored. The data, the mapping is estimated. So there's still a lot of fundamental science work and exploration to be done everywhere, frankly, with most of the data coming from oil and gas development regions. So why is it so exciting now? Well, there's multiple lines of development that have come together to make geothermal anywhere an exciting prospect just in the last few years. And in fact, it's so recent that you won't find hardly any publications yet on the new developments. What's happening is being conveyed in meetings like this, in a couple of key geothermal conferences and such. But what's really come together are the advances in oil and gas drilling and the supporting technologies, which enable you to drill faster, more accurately, and that saves money. And then you also have ongoing advances in the technology of converting heat to electricity. And then finally, you have the urgent need to decarbonize our power supply. And it manifests in a lot of ways, including direct stakeholder pressure on corporations and such. So all that's coming together now to give us the potential for geothermal anywhere. So what are the advantages? Well, especially compared to other green or renewable resources, geothermal is a base load. It's on 24/7. And that's a very important differentiator between from wind and solar. It's also extremely resilient to disasters. You have no supply logistics chain to worry about. Weather generally isn't going to affect it. It is low to zero carbon. It can even technically be slightly negative carbon in its footprint. The low carbon being generally the hydrothermal or conventional geothermal. The modern geothermal anywhere is mostly closed loop, and that, if done appropriately, will be zero carbon. Geothermal is already price competitive, so that's a good thing. And crucially, the geothermal anywhere paradigm differentiates from conventional geothermal in that anywhere word. So you can drill where you want the power. I'll talk a little bit more about risk and accuracy in just a second. But also don't forget, and this is already better known outside the US than inside the US, direct use of geothermal heat is actually more efficient than converting it to electricity. So if you're using it for industrial or agricultural purposes, or just to heat and cool houses and buildings, that's actually a more efficient use. But the demand right now in the development is focused more on providing electricity. So what's the potential? The potential is enormous. If you look at a typical S-curve of adoption, which applies to any new technology, think cell phones a decade or two ago, which were down here, now they're up here. And it's basically a curve that shows early adoption as a technology emerges, the adoption by the mainstream, and finally a mature level of technology. Conventional hydrothermal geothermal is a fairly mature technology. It's still advancing and improving, but it's a relatively mature technology. Geothermal anywhere is right down here at the inflection point now. So it is taking off and developing extremely rapidly right now. So as has happened multiple times, we're on the edge of an energy revolution and a new paradigm in supplying energy to the world. And the next couple of years in particular will really see very fast development. Texas geothermal, just a blow-up map of this. We have a lot of different geology, tectonic activity and such, and I've already talked about multiple leases coming into play. But we've also got a very good regulatory, government, and business climate for development of geothermal. And those things do matter. Slight changes to government policy allowed Texas to shoot into the lead in the US in providing wind power to the grid a decade ago. And similar small adjustments like that in government policy, in the law and such, can make a big difference in the development of geothermal. On the business side, the main things that the other thing besides geography that slowed things down for the past 30 years has been fairly high upfront costs. But now with significant private investment, that's less of an obstacle. And you must remember that on the back side, once a plant is built, you've got no fuel costs. So the operations and maintenance of a geothermal plant is relatively low compared to a fossil fuel plant. This technology can also be used very well to store energy and level out wind and solar. So that's another good use. And I've already mentioned direct use case. And in all these areas, there's still a lot of fundamental science and technology to be done that can help industry and government essentially buy down the risk of geothermal development across the board. So speaking of risk, a little bit more on risk. So I keep differentiating conventional geothermal versus geothermal anywhere. Conventional geothermal being essentially virtually all the world's installed geothermal power systems, where you're tapping into a natural hot water or steam system in the ground. This has a similar risk profile to oil and gas drilling in that you've got to hit the permeable zone right on, and a 10-meter or 100-meter different offset may mean a dry well. So you're still searching for that fluid. Geothermal anywhere is a different risk picture because you're looking for the heat in the rock, preferably dry rock without formation fluids, but heat in the rock. And the heat in the rock does not change very rapidly over scales of kilometers. So having your well drilled 100 meters away from a current position is not going to measurably affect the success of your project. And also, since you're drilling for temperature in the rock and temperature increases with depth, you're never going to miss your target. You're going to hit the temperature you're looking for. The question is, are you going to be in the rock type you want when you get to the temperature you want? So that still involves old-fashioned geologic detective work, which you'll hear a little bit more about later. And there's other associated risks along these lines that I'll mention briefly. The players in this revolution are mostly startup companies. This is a small sampling of, let's see, in this case, North American startups, but they're leading the charge with some support from the very small academic community, of which we're a sizable fraction right now. But the academics are leading the way with private investment. In the US, the Department of Energy is the traditional funder of research, and they're still going strong, if not growing, on their funding of research. But in particular this year, the Department of Defense, the military, jumped in a big way with the largest call in history at one time for new geothermal power plants, with a call for 6 plants around the US. They are starting to let the contracts for development of those plants issue now. So that's a major change in the landscape here in the US. And then we can go into that in questions and answers, but geothermal has a significant advantage to the military. Okay, there's also all the major companies are involved in this now. We'll talk more about this perhaps later, but we finished a design study for a plant on the south side of Houston for the military. That's essentially ready to build if the military can create a power purchase agreement on that one. Other issues which come into play, again, this is for another discussion, but water resource impact and induced seismicity potential are the main issues that get brought up by the public. I think those will be generally very small risk, essentially negligible probably for closed loop for the geothermal anywhere, low to moderate for conventional hydrothermal development. Don't forget about the legal issues. This in the US, this varies from state to state. Elsewhere in the world, it'll vary from country to country, but it makes a big difference. And this new approach of going for heat in the rock may require new law. And with that, I'll stop with questions, but as Jackson mentioned, there's also geothermal in space. So if you're interested in those areas, get in touch with me. There's no boundaries on doing geothermal, and there's active geysers on multiple bodies in the solar system. So thank you very much, and happy to take some questions at this point.
Great, thank you, Dr. Wiesen. That was really interesting. If there's any questions from the audience, if y'all can put them in the chat, that would be great, because I don't believe you guys can take yourselves off mute. But maybe while folks are thinking of those, I've got a question. So we were talking about geothermal development, the conventional versus the new technology. And you showed that, and someone put it in the chat already here, the fracking for geothermal anywhere. Could you just explain a little bit how fracking for oil and gas is different than the fracking that'll be used for EGS technology?
Yes, that's an excellent question. And it is, again, perhaps the dominant issue that concerns people in this regard. We really need better words. Fracture creation, stimulation, those kinds of things are a better fit. So in oil and gas, you're looking to create the biggest, deepest fractures you can. And in geothermal development, it's a much more limited set of development of fractures, both in time, space, and scope. So in geothermal, and there's various methods of how you go about creating fracture networks, are very long laterals so that you have enough surface area to transfer heat from the rock into a wellbore. Whole nother subject area. But in geothermal development, you're looking typically to create a set of fractures, say, between two parallel wells. So they're relatively close together. You want fractures that are as uniform as possible and only extend between those two areas. That's very, very different by an order of magnitude or more from oil and gas fracking. So you're doing a less intense fracture. You're trying to control them to a much greater degree. And don't forget also, one of our research groups here runs the induced seismicity network for Texas. And the induced seismicity from the oil and gas field work over the last decade, our understanding of it has advanced tremendously. And what we found is that in most cases, it's the re-injection of the wastewater from oil and gas production that causes the bulk of the seismicity. Although in some basins, it is the actual original fracking. But we have monitored the one test well in Texas that was done last year and this year, creating a 1 kilometer tall vertical fracture. We monitored that with an array of seismometers and observed no measurable seismicity from that project. And that's what we've got to do. That data went straight to our public website. The only way to reassure people is to be open and straightforward with the information. So a little bit of a long-winded question. I see it also came in acid matrix or proppant. Generally, so far on the methods that are being exploited, largely neither. Proppants are being explored, but the test project we were on, which is led by one of the startups on the slides I showed, known as Sage, they're a Houston-based startup in this area. They have their own patented method of doing gravity-based fracture development. So they created a 1 kilometer tall vertical fracture, and then they simply pumped water into it to open up the fracture, but without getting to the point of fracture propagation pressure. Let the water heat up, and then just backed off the pressure and let the fracture close, push the heated water back out. So they are deliberately they're only using pressure to open and close the fracture. And what they found in particular was cycling it in a huff and puff method was the most efficient extraction of heat. So the method they're exploring will be just cycling a fracture indefinitely between zero pressure, letting it close most of the way, and opening it up to just below fracture propagation pressure. So hopefully avoiding proppants, avoiding the fracture, the acid type of method. But this is an area of intense development. So new ideas are being tried all the time. And in the other main approach to this is drilling very long laterals. Malcolm Ross can talk more about that. But if you don't do fractures, you've got to have a very, very long well bore to have the surface area you need to transfer heat from rock. And so that's the other main approach to this. More questions, please. I don't see any more coming in, but I'll stick around if any do come in as redirects. And let me turn it back to you, Jackson. And I'll, yeah, stop sharing. Okay.
And, that's such an interesting topic. Maybe it'll be something we can cover next year, more in depth, the specifics on the fracture methods.
Sure thing.
So our next researcher is Dr. Shubhajit Bachada. He is an expert applied geophysicist and petrophysicist. The work he has done in seismic interpretation, petrophysical modeling, fault and fracture characterization, and much more has led him to his interest in geothermal, which I'm very grateful for. And today he's going to share with us his work identifying basins here in Texas, which are prime candidates for geothermal utilization. So please feel free to take it away, Jake. You're on mute there. Perfect.
As always. Let me know if you can see my screen.
It is in presenter mode.
How about now?
Perfect.
Good. Thanks, Kane and Jackson, for setting the stage, and so that I can take independence to go and deep dive, right? And so I will be talking about how geology plays a role into the geothermal exploration, both at a regional scale and local scale. This is a combination of two different studies we did, one for the entire state of Texas and one for a very, very local case study from southwest of Houston that Kane was talking about. So a couple of important things to take away from this presentation is that we are dealing with different rock formations, different basins, and there are different technologies for well completion, which implies there are different geothermal potential and output. One formation can be explored geothermally in many different ways, whether conventional geothermal or EGS type geothermal, and that would imply different types of geothermal output, right? And so Texas has a wide variety of geologic settings. We are dealing with both sedimentary rocks, non-sedimentary rocks, different types of thermal conductivities, and different temperature settings. And therefore, there is no one-size-fits-all approach to the geothermal potential assessment of the state. And this is true for other states and countries as well. And therefore, we do think the subsurface geologic and geophysical characterization is one of the keys to regional and site scale studies. And we do really believe that good characterization is really important for good techno-economics and de-risking the project. And so these are important. These type of characterizations are important to select suitable areas for drilling, for geothermal wells, estimate the heat resources, optimize techno-economics, as well as de-risk some of the prospects, right? So in the first few slides, I will talk about a report that many of us at the BEG and UT Austin, we put together. And this is the report that's called The Potential of Geothermal Energy in Texas, or the Future of Geothermal in Texas. And it was funded by the Mitchell Foundation, led by Jamie Baird. And so this report is publicly available, and it has many chapters into this, starting with the geology, engineering, and many different policy aspects of it. So this establishes an update of the understanding of the geothermal potential of Texas from both conventional point of view as well as geothermal anywhere point of view. And we did some basic calculations there, and the total amount of heat that we have in the rocks in the upper 10 kilometers is huge. It's around 1 million exajoules, and that can supply the electricity for many different entities for many years. And so here is the Texas map, or the geologic map, and those stars are showing where we have these different geothermal potentials, right? So we're dealing with sedimentary basins where oil and gas companies have been drilling wells for the last 100 years. And then you have other areas where you have non-sedimentary rocks, like volcanic rocks, granitic rocks. So on the west side, starting with El Paso side, we're dealing with mostly your non-sedimentary rocks on the Basin Range province. And here we have high geothermal gradient. And in fact, some of us are working on a project in the Presidio County now, that's in the border of Mexico and Texas. And so we're going to look at the geothermal potential there. Then we have the famous Permian Basin in West Texas, and that's where we have this a lot of sedimentary rocks, deep sedimentary rocks with high temperature. We also have Gulf Coast of Texas, and Gulf Coast, as you know, very uniquely positioned because of its high overpressure. Good for conventional hydrothermal, geothermal. Same thing we see in East Texas, very high overpressure, high pressure, high temperature in the subsurface rocks. And then you also see some potential in the panhandle of Texas and north central Texas near Dallas. So there are different basins, different rocks, different types of geothermal potential. And so, but we start with the foundational data, that's the bottom hole temperature data. And so thanks to these oil and gas companies in these sedimentary basins, there have been millions and millions of data points that are available. And so we need to use that and process those properly and generate the heat flow maps that you can use to understand the potential. And you can see the red colors here that shows the hot spots, some of those in the west, some of the in the El Paso area, some in the East Texas, and some on the Gulf Coast of Texas. So these are the areas where we have some good potential, as you can see. Then after looking at this overall temperature data, we looked into the geologic cross sections, the basin geometry at a large scale, looked at the Permian Basin, Gulf Coast, how those are similar, dissimilar, and how the rock formations are deposited, looked at the map distributions of different formations, Frio, Vicksburg, many different formations, and how the temperature varies in those different formations. As you go deeper, different formations have higher temperature than others. And you also see it's not just the vertical variation of temperature, we also see sometimes the lateral variation with corresponding to the formations, right? And then beyond the temperature, and we also looked at the thermal properties like thermal conductivity, and there are different types of rocks with different thermal conductivities. We found the salt has a high thermal conductivity. We have quite a bit of salt in the Gulf Coast of Texas as well as in East Texas, and so that could be a good spot for geothermal. But then you also looked at some other petrophysical properties like porosity, permeability, how those are related, and how can you use them for heat flow, for the reserves estimates. And this also can help us to know whether we need to fracture a rock or not. If it is highly permeable, we may not need to create a fracture network, but if it is really tight rock, we may need to create a fracture network, right? And so there are a lot of different aspects that we need to look at from the subsurface point of view, starting with a big scale understanding of the basin geometry, knowing the rocks that are present, how they're deposited, and looking at the temperature, thermal properties like thermal conductivity, as well as other petrophysical properties like porosity, permeability. So these are for the exploration part, right? And then we also looked at then what's about induced seismicity. So at Bureau, we have this group called TexNet, and they have been analyzing seismicity data from different basins in Texas for the last several years, and many of this data are publicly available. And here you can see these different basins, starting with the Delaware Basin, Midland Basin, then the Gulf Eagle Ford, and these dots are showing that where we have these different earthquake locations. And so, and this can happen due to reactivation of existing faults and fractures, right? And here we are showing many different fault locations. And that can, and many of these faults are closely associated with the location of the earthquakes. Now, that gives an understanding why detailed subsurface interpretation is important, so to de-risk some of the prospects. So we compared and contrasted many different formations and opined on which formations are good for conventional hydrothermal geothermal or which ones are good for EGS type geothermal, and talked about the risk in different basins. Different basins have different risks. So that's we need to keep an eye on. So now what I'm going to do, I will now talk about this detailed case study that we did in southwest of Houston. So this project was funded by the US Air Force, and we worked with the SAGE Geothermal geosystems for this work. And so the ultimate objective of this work was to produce 3 megawatt of electricity at the Ellington Joint Reserve Base. And this is near Houston, Harris County. And he's on the geology-wise, it is on the Gulf Coast of Texas. And if you zoom in, what we found out, there are actually 3 existing oil and gas fields here, like Clear Lake, Webster, and Olcott fields. And these are the fields that have been producing oil and gas for the last several decades. So you have quite a bit of data from this area. And this was the proposed drilling site. Now, this case study, in a way, will help us demonstrate some of the applicability of the oil and gas data, infrastructure, and workflow for geothermal. So here is a geologic cross-section that you can see. So it goes from A to A prime, that is coming from the north of Texas to the Gulf Coast of Texas. And as you move to, we look at these cross-sections, the different colors that represent different rock formations, and you also see some very irregular features like this type of salt. And as I said before, the salt has higher thermal conductivity than many other sedimentary rocks. And associated with the salt, we also see many large normal or extensional faults. And what we know that some of these faults on the Gulf Coast have higher thermal anomalies than other faults. And that kind of because of the fault characteristics, the fault sealing, and many other aspects. So we looked at this overall geological pattern. A lot of studies have been done for years. Now we looked at this big scale pictures. And then we also looked at the overpression. In many formations on the Gulf Coast of Texas are highly overpressured. And that's coming from the decompaction and a lot of pore volume water that is present there. And back into 2012, USGS published a map of the high pore pressure areas in Texas and Louisiana, onshore and offshore. And wherever you see red, that indicates you have this higher pore pressure, like where you have more than 0.7 psi per foot. So then, so those are the areas in the Gulf Coast. As you can see, there's a high pore pressure. That's a good thing, and that can help production of the formation fluid. We can look at the mud weight data, and you can see how the drilling mud weight, they increased from around 8 to 9 ppg of mud weight to 16 ppg of mud weight within a depth of a few thousand feet, and that's where the pore pressure overpressure starts. Then after looking at this, we looked at the geothermal gradient into the local site we are working on. We had around 24 wells nearby the proposed drilling site, and so we compile the temperature data. And as you know, the BHD data that we get is not always the accurate representative of the true subsurface temperature. So we looked at many different other methods. How can we correct the temperature effect? For example, the effect of the mud circulation. So we used Harrison's correction for this. And by doing this correction, we could see, depending on the depth and the location, we had at least 2 to 17 degrees Celsius difference from the bottom hole temperature-based temperature, basically. And the geothermal gradient here is around 32 degrees Celsius per kilometer. Now, we have some deep wells that went down to around to 12,000 or 12,000 or 15,000 feet depth. So we are reaching around 160 Celsius at around 4,500 meters, if you look at this graph. So after looking at the temperature, so we can understand, okay, this is kind of temperature range we are reaching, and then based on a collaborative understanding with SAGE, we are asked to find the formations that reaches around at least 150 to 200 degrees Celsius. And so now, using temperature as a constraint, we found which formation has that ability, has that type of temperature. So we looked at the formation properties. Then we looked at, for example, the porosity, permeability, temperature, depth, things like that. And we found that in this case, in this specific study, we found the Wilcox formation in onshore, that combination of sand and mud has actually reaches the temperature of 200 degrees Celsius, around 16,000 feet, but it has lower porosity, lower permeability than the upper sandstones like Frio and Vicksburg. So based on this technology that was planned to use, based on the techno-economics on the specific technology, this Wilcox formation was deemed appropriate. But that not to say the other formations like Frio or Vicksburg have no geothermal potential. As you know, there are some companies that are actually trying to exploit the heat that you can get from the Frio, but using different technologies. So here is a plot of the porosity, permeability, and from 6 different wells. So what we found that as the temperature increases, the depth increases, the porosity, permeability is reducing in the Wilcox. So we wanted to know why. And this is why some of the detailed scientific experiments and simulations are needed. And what we found that there is a really large drop in the porosity of the rock as the temperature is increasing, going up to 200 Celsius. What we are finding out that a lot of the primary porosity in the rock is reducing a lot because of a thing called diagenesis. We are seeing a lot of feldspar dissolution, some precipitation of kaolinite siderite, which is why we are seeing the primary porosity is reducing. What we have mostly is a secondary porosity, and that makes the case that we may need to fracture these rocks. So now what we did after looking at petrophysical properties, now we wanted to look at make these maps of these formation properties and the formations. So we used, we had access to a few 2D seismic lines, and these are very limited seismic lines we had. And old 2D seismic, so we come up with a workflow to interpret this old data that is very valuable for this project. And we interpreted the seismic data, identified the formations, Frio, Vicksburg, and our target Wilcox, as well as some of the faults, some of the normal faults that are associated with them. What we found out that these faults that we see here, they're within 1.5 to 3 miles from the proposed drilling site. So now we need to think about how we are going to design the well geometry and probably the stimulation of the well, right? And because, as I said, we had limited seismic data, we looked at the LiDAR data that was published by the USGS, and we compared their interpretations with ours. And what is this? As you can see on the left-hand side, we had a lot of this. We had these seismic lines in different colors, and then different faults that were mapped. And then what we see some good correlation between our faults on the local side with the USGS faults. But then what we also did with the help of TextNet, that group, they put some seismic stations. It's like these triangles represent those seismic stations that are put nearby those fault locations and the drilling site to monitor any type of seismicity that can occur. So we did the baseline seismicity characterization before drilling and fracturing the well. And so when we anticipate we may have to do this thing again when the well is being drilled and completed. That way we know and that we know how to optimize the engineering completion. So let me summarize this thing here. I discussed the regional geothermal potential of Texas in different basins that can have both sedimentary rocks and non-sedimentary rocks. And it shows how some of the proven systematic workflows that we use in the oil and gas industry regularly, how we can apply them for an organized geothermal site characterization efforts. And in this specific study, we found the lower portion of the Wilcox has the potential for suitable heat generation. And there are a few large faults in the study area that we need to characterize in more detail to de-risk the prospect. And so new drilling, new completion technologies, including hydraulic stimulation, may be needed for electricity generation in that site. And thanks to Mitchell Foundation, thanks to US Air Force for funding this project, thanks to our colleagues at the Bureau for sharing some of the core data, and thanks to Schlumberger for donating a software to UT Austin. And thank you to you all. Any questions?
Thank you, Jit. That was very interesting. There was something there that is really exciting to me because it sounds like, as our understanding of the subsurface and these different basins, it seems like there's more opportunity for geothermal than we previously thought, right?
Yes, I would agree with that. And so we have, I mean, now with this new data processing technologies and new data that is coming up, especially from the shale wells in the last 10 years, there's a lot of new data and good quality data that is coming up. And so if we reconcile all this data and harmonize them together, I do think we can see a much higher potential than we have previously thought.
Great. That's great news for us. We do have a question in the chat before I get to one that I had. So what kind of completion systems, casing size, ECT?
In this case, as this project in the well has not been drilled. So I cannot really tell about the completion systems, but what I do know about the technology that we are supposed to use called gravity fracturing. There are some publications online. The idea is that going to basically create a vertical fracture now, a vertical fracture through which you can basically circulate your fluid and basically generate, basically exploit the heat. And so they're going to use the gravity fracturing method for this. And of course, I mean, it's geothermal well, so we'd expect, if you're going to get high flow rate, we are supposed to use a larger diameter of the borehole. What it means, the casing size should be also enlarged compared to regular oil and gas wells.
Very good. And then the question I had, and this, I'm a social scientist, not a geologist, so apologize if I heard wrong, but when you were talking about tight rock in Texas, and you were talking about that perhaps we wouldn't need to frack to begin some of these geothermal systems. Where is that possibility in Texas?
Can you please repeat the question so that I can understand it fully?
Earlier in the presentation, you had mentioned that not all of the geothermal resource that you see in Texas, we wouldn't necessarily have to access through fracturing. So I was just curious where those basins were.
No, that's definitely a good question. Again, it varies vertically and it varies laterally, right?
Oh.
And so there are certain areas in Texas where we do think that there are formations that contain enough for a pore volume of water that is at high temperature and also high pressure that you can exploit, that you can basically produce, and we can recycle that, right? There are areas for, and some of the cases we can even do some sort of closed loop geothermal, but not necessarily we need to fracture them. I do think there are areas in the Gulf Coast of Texas as well as East Texas. We have some of these possibilities in some of the sandstone formations. Let's say some of the Frio, Vicksburg, Wilcox, some of those, especially where it is higher temperature, higher pressure. For example, back in the late 70s, Bureau drilled a well called Pleasant Bayou wells. And those are a little considered sometimes little outlier because of multiple different reasons, but they did produce around 20,000 barrels of water per day. And we need that volume of water. At least that kind of volume of water, but also in these areas in the Gulf Coast, Texas, as well as East Texas, we have salt bodies, right? And salt has high thermal conductivity. So if you can drill a closed loop geothermal system, you can even exploit the heat from the salt bodies itself. And I don't think we need to fracture salt. So you have different possibilities. It depends on the different companies, what's the perspective and what's the strategy, and where is the company's footprint, right? Mm-hmm. Those types of things. Yeah.
Got it. We had one more question come in. I'm not sure if you want to tackle it or maybe someone else, but
I can do some of that. Yeah, this is a good question, actually. And a lot of people have been thinking about it. And some people have been working hard. Is it really feasible to use the previously used oil and gas wells that are depleted for geothermal. I think this is a really good thing to do it if we can utilize these depleted oil and gas wells. But the question is about the wish versus the practicality. What is, I mean, we can definitely use the data from these wells. We can re-enter these wells, collect a lot of high resolution temperature data. But again, thinking about some of the engineering factors like the well diameter, the well integrity, the well that has been existing for 30 years, we're going to use for geothermal for next 30 years, the scaling, many different aspects of there that does need to be studied in more detail. And again, one site does not represent all other sites. There are many wells that have been drilled in the shale basins very recently. We should expect they can have higher well integrity than the wells that are drilled in the 50s. So again, different basins, different sites, different potential.
I'll chime in a little bit on that too. It's an open question, but an area of intense interest from all the field operators. So from my perspective, a couple of things. Jed already mentioned, what's the status of the well? It's going to vary tremendously. But also, most oil fields just barely get into the temperature range that's viable for electricity generation using geothermal. So assuming you're on the low end of the temperature range, which is around 150 C or 300 F, you need to flow between about 10 and 40,000 barrels a day of fluid to generate a few megawatts of electricity. And that can be very difficult or impossible to do on a typical oil and gas well, which necks down as you go deeper. Now, there's possibilities of using other fluids instead of water, particularly supercritical CO2 might work in a narrower well, but water at like a 5-inch or so well bottom diameter, you're going to have just too much parasitic drag. So there's factors to consider. Are you going to need to over drill? Or are you going to need to deepen a well? But also, again, that key technology of drilling faster and accurately has increased so much these days that it might be that it's cheaper to drill a new well in an existing field than it is to rework an old well, because you can drill so cheaply now. And you already benefit from knowing the rocks and the lithology so well if you're drilling in an existing field. So it's an open question. We need field projects and experiments to really answer this question. But it's one of the leading questions that's on everybody's mind right now. So thank you.
It almost seems like the potential for the oil and gas well reuse right now would more be for storage or direct use applications that are at a lower temperature than needed for electricity production.
Yeah, and that's viable too. Again, an area that's really under researched so far. So there's lots of room in almost all aspects of this for some good basic science and engineering research.
You might also consider the oil and gas wells for reinjection rather than production. And you could use 3 or 4 of them where you have one new production well that's big enough in diameter, then 3 or 4 of the smaller ones to do the reinjection.
Sounds good. And I guess this is a good time to introduce Dr. Malcolm Ross, but also thank you, Jit, for giving us that talk today. It was real interesting, and appreciate the time.
Thank you very much, and the listeners.
Malcolm, he just tuned in with us here, or chimed in there, I should say, but he, besides being a member of the Bureau at UT Austin and a professor here, he is also a professor at Rice University down in Houston, Texas. He's been a strategic advisor to a number of startups, including several in the geothermal sector. Malcolm and I also worked together for the Texas Geothermal Energy Alliance, where we had a very successful year getting 4 pieces of geothermal legislation passed. His current work in geothermal is investigating the techno-economic dimension, and he has developed a modeling tool he is going to share with us today. But before he does, I also wanted to mention a project he is working on with Project Innerspace, one of the places that I also work with. And It's a really awesome project because the implications are so global. He calls it Project Canary, and is a techno-economic feasibility study for the conversion of coal plants to geothermal plants. And it's extremely exciting. And hopefully, Malcolm, you can maybe talk about that next year for the next Geotheroom. So with that, I will let you take it away.
Yep. Thank you. Make sure everyone can hear me okay?
Yep.
Okay. So yes, so I am going to speak about trying to quantify some of these things that the previous speakers were talking about using a techno-economic modeling tool called GeoPhires. We have upgraded it from version 2 to version 3, otherwise known as GEOPHIRES-X. And this was released to the public last week, I guess, or just over a week ago at the Geothermal Rising conference. So this is based upon an existing tool called GeoPhires version 2 by Koenraad Bekkers, my co-author. And it is being done as an open source development project using a public library. So this is an attempt to try to make all the source code available for what I'm talking about, with the hopes that there will be other contributors to it rather than just Koenraad and myself. And I put in a URL here and a QR code where you can connect, look at the code, download the code, or also connect to a web-based, browser-based version of the tool. And I'll talk about all of that. First, I should explain GeoPhires is it's an acronym for Geothermal Production Economically Simulated. It's really about combining reservoir, wellbore, and surface plant technical models, essentially like a digital twin, and cost correlations and levelized cost models to build a model of the capital and operational cost, energy production, levelized cost for a geothermal plant. It can also do direct heat and combined heat and power generation. So we took this code, version 2, and rewrote it as an object-oriented program. So what is object-oriented program? It's a way of structuring code to make it more modular, encapsulate data and behavior together in objects, abstract real-world entities from those objects, or characterize real-world entities as in those objects. We can do multiple subclasses. That's called polymorphism. And it's, in theory, easier to maintain. Why not object-oriented programming? Well, it's complex. There are some performance overheads for it, and there's a kind of a steep learning curve to it. So really it came down to us trying to make a choice. Do we stay with sort of linear procedural code to make it easy for people to develop in it? Or do we go to this, take advantage of these options in that are available in object-oriented programming? And I put up this word cloud only to remind everyone that geothermal is a very dynamic environment right now. And Dr. Wizian spoke about how, for him, he's never seen this kind of momentum. Well, within that momentum is a bunch of variety that's totally new. This closed loop, for example, lithium mining, a bunch of new direct uses like hydrogen production, et cetera, et cetera. So we're in a very dynamic environment. And if you're trying to maintain a source code that is a digital twin of that environment, all of a sudden, modularity, encapsulation, abstraction, polymorphism, and maintainability become very important to be able to keep up with that change. And so that's why we went down this path. It turned out not to be that difficult. This is a figure from the version 2 software where you can see basically that we're already within the code thinking about objects. So there's an object, a reservoir that gets simulated first, and then that reservoir gets penetrated by well bores. Those well bores then produce energy to produce heat to the surface, and the surface plant takes advantage of it, either makes electricity or direct use, etc. And then all of those things are summed together in a module for calculating costs, and then the costs and production, and then there's the techno-economic calculation. So that was all in version 2. So we simply took those 4, 5 things and made them into these objects. So there's a reservoir object, a wellbore object, a surface plant object, and an economics object that get operated in a very specific pattern, which I'll show you in just a moment. Once those objects are instantiated, the calculations are made, then we can produce the output result. So every object has the same structure. It's basically has parameters that describe it. A reservoir might be, what kind of rock is it? How deep is it? What temperature is it? The wellbore might be, what's the diameter of that wellbore? How deep does that wellbore go, etc. So every object has a set of default parameters that the programmer puts with it. So it gives it a logical value. Then the user has the chance to modify it, and they can leave it alone if they think the default value is a reasonable value. We tried to assign reasonable values for everything. So you just modify those things that are unique to what you're doing. And then we have algorithms for calculating whatever needs to be calculated for those objects. And those things are done in a very specific way. It starts with initializing everything with those default values. So we initialize the reservoir, the wellbore, the surface plant, and the economics. Then we do the modification of the parameters with the user values. And then finally, we make the calculations and then make the output. So now we get into this advantage of polymorphism. I'm going to use ground source heat pumps. So right now there isn't ground source heat pumps in the GEOPHIRES-X. So how would we do that? Well, we've got this object, the generic object reservoir, and we already have some existing subsets of that, sub-objects of that inherit all of the characteristics of the abstract class of the reservoir, but also have their own parameters and their own calculations stored with it. And for a ground source heat pump, we simply need to add a new reservoir, in which case it's the sort of shallow soil, the first sort of 100 meters, where we might put the array of pipes that make this ground source heat pump. So that then brings the wellbores object, and we have some pretty simple well bores, but for a ground source heat pump, we would need ground loops. So we'd need the pipes that we lay out in the ground, and we need to characterize those. How big are they? What's the flow rate through them? How long? How deep, etc. And then for the surface plant, yeah, we've got a whole variety of surface plants already built in, including direct heat and organic Rankine cycle, etc. But for a ground source heat pump, we need to design a new module that descends off of the surface plant and is the ground source heat pump. Every parameter is smart, and for the coders here, you'll recognize Python code. Everything is in Python. But for those that aren't, I just want to put this box here that shows you, for example, the parameter reservoir depth, which is a object. It's a part of the reservoir object. You can see it has a value. This is the value, which is the same as the default value to start, but this is the value that the user might change. But every one of the parameters knows what its minimum, maximum, what its units are, what its current units are, error messages, etc. So every parameter is not just a value, it's a bunch of information about the value as well. And that becomes important in just a moment, which I'll show you. The code runs exactly the same as GEOPHIRES 2, except all of the cost parameters have been updated to 2023 kinds of costs. But the input files are the same. And other than the costs, which are slightly variable due to inflation and so on, the user can now choose other input units. So if you want to work in feet or pounds per square inch or Fahrenheit instead of Celsius, etc., you can now do that and when you declare your values, you can just say, 300 F instead of 150 C. And it will automatically on the fly make the conversions for you. It also allows you to work in different currencies. Right now, it's working in US dollars, and all of the cost estimates are in US dollars. But you can now specify your own currency, whether it's euros, pesos, etc. And it will connect to a foreign exchange and do the conversion to dollars behind the scenes, make all the calculations, and then when it produces a result, it will convert back to your currency. So it will also can display the change of the output in the report, so that the report doesn't necessarily have to be in meters, Celsius, etc. It can be in whatever units you want it to be. And this is all about accommodating our international friends who want to use this with their own set of parameters. What are the technical features of this new version? There's lots of subsurface design. So we've designed the ability to handle closed loops of various kinds: single bore, coaxial or U-shaped, or multi-bore, multilateral kinds of setups. We can add working fluids now. You can either use water or supercritical CO2. And then in terms of add-ons and outputs, we have absorption chillers, direct air capture, using geothermal energy, and then district heating with peaking boilers. These were just the ones we choose to add. Once we had this object-oriented framework, it was easy to add these things because we just descended off of, for example, surface plant, and added just the values that matter for absorption chiller, direct air capture, etc. Now, if your favorite technology is not listed here, I invite you to write some Python code and submit it to the GitHub, which you will see when you go to the tiny URL .com/geofires. Within the tool now, we have a heat and place calculation. So heat and place calculation is really just a very simple calculation. There's about a dozen or so values that you can put in, and it will produce an output forecast for you. This is sort of when you don't have a lot of information, you can do a 30 plus or minus 30% calculation with just a handful, a dozen or so calculations. And this is what the inputs look like. It's just a text file. But what you can also do with this is a Monte Carlo simulation. So these are the inputs for the Monte Carlo simulation, where the formation porosity, we don't know what it is. We know it's somewhere between 9 and 28, or we don't know the reservoir area. It might be between 50 and 120 kilometers. The reservoir thickness might vary between 0.12 kilometers and 0.29 kilometers. We might have some uncertainty in the reservoir temperature and so on, and we can essentially plug these in as random values that a program generates, and it will produce an output of the recovery factor, heat, and producible electricity, and it will do 250 iterations. In this case, you could do thousands of iterations if you want, and then it will calculate those values, so recovery factor, available heat, producible heat, and producible electricity, and it will produce 250 of these simulations, and then you can do the statistics on that. So, for example, the producible electricity number, the minimum was 0.8. That's a really bad set of random values. But it produced upward on the upside 44 megawatts and a median of 8, and you can actually then put that into a statistics package and produce a probability distribution where the highest probability in this case, and for those set of range of parameters, is somewhere about 10 megawatts or so. We provide to you a set of examples. These are just the examples from version 2. And you can see there is various reservoir types: enhanced geothermal, hydrothermal, various reservoir models, different kinds of fracture models, and simple linear sweep models, percentage drawdown models. Notice that you can also provide your own reservoir basically bypass it by providing a table of data that's just the output temperature data. And you can actually connect to Tuf2, which is a public domain reservoir model, and run Tuf2 in the background. Then you have the outputs here. Here's a supercritical ORC. Here's direct use. Here's a combined heat and power, a subcritical ORC, etc. And then various economic models, simple models to very complex models, all of which get described in a text file like this. And again, you only change the things that you want to change from the default value. And you can build there's over 100 values that you could change. You can build a file like this that has 10 or 20 and do a simulation. And this is what the simulation looks like. I could just run it for you. This is a command line interface, and you can see it's just run it a Python program, gives you some warnings, and then it produces some outputs, some tables of data that you can see here, and then some simple text. And so what I want to show you is a little more detail on that. So here are some of the text-oriented outputs. So this, I think, is example 1. You can see it's end-use option electricity. It produces about 5.5 megawatts for that set of inputs that we provided. It gives you a levelized cost. So for that set of inputs, the levelized cost is 9.3 cents per kilowatt hour for 2 production wells, 2 injection wells, etc. These are a bunch of the other inputs and some of the outputs. So here's the output. The project net present value is negative on a 30-year project. It loses $38 million over 30 years. And so the negative IRR return, negative, really low rate of return, this is a loser project. You would not do this project. So it's your job to get back into those values that you changed and figure out, do I need to drill more wells? Do I need to make the hole bigger? Do I need to go deeper and hotter? All of those things. This tool allows you to play with those things until you get to an economic model that your investors are going to be satisfied with. And by the way, this is also capable of doing this with Monte Carlo simulation. So you could run 10,000 simulations with a bunch of different inputs and figure out which one produces the best value. I won't go through all of these, but I also wanted to show you that it produces lots and lots of information here, but tables of data, including every year what the thermal drawdown is. And in this case, the thermal drawdown is actually positive. At temperature actually goes up, as you can see here. What's happening here is you're drawing fluid out of the reservoir, and it's drawing hotter fluid from deeper to replace it. And so that's why the temperatures are actually going up. And here's the first law efficiency, for example, is still less than 10%. And then here's the web-based version of it. You have the ability, if you go to this URL, to basically do what you would have done, but in a browser with inputs where you just type in the values and it knows what the expected units are, and you hit run GeoPhires, and it produces a table of results exactly like the table of results from the command line, but for the things that are over time, it actually produces graphs for you instead of just tables of data. So that's all I had for you, but I need to point out that this is a project supported by the National Renewable Energy Laboratory, validated by the National Renewable Energy Laboratory, and these are so far a couple of the contributors who have provided source code to us that we have incorporated, and we hope that you have a source code that you would like to contribute as well. So I'll leave it there. Looks like there might be some questions in the chat. Jackson, do you want to relay those to me?
Yes, I was just going to say thank you for that, Malcolm. You know, I've heard you talk about GeoPhires in person many times before, but it was great to actually get the presentation from you. There isn't any questions in the chat right now, but I had one just I wanted to clarify really. So with GeoPhires, anyone can use it, of course, but so if someone has the data, the subsurface data for their region of the world, they need to upload it to GitHub first to be able to? No, okay.
And in fact, you just need to download the code and modify the example files using your unique values for your part of the world, and run the code and get your results. That's it. And all that remains local. If you decide, oh, you know what, I need to write some code, you could write that code on your own machine and just run it, and that would be fine. You do not have to provide your new source code back up to everyone else, so that you can do proprietary things here. That's not the sort of community-oriented democratization of information kind of thing we're trying to accomplish, but there is nothing to stop you from doing that.
Got it. But a great tool, certainly, you know, and I when we start to look at some direct use projects around the world, I know I'll certainly be using this.
Right, and I should also mention, so you mentioned Project Canary. So Project Canary is essentially a GIS project, digital mapping project, where we will try to compile globally, or at least starting in Texas and then maybe North America, and then reach on out from there with the help from Project Interspace, where we gather all of the inputs that basically get written to this text file automatically. So you have a set of point data, be they coal plants, be they cities, be they, you know, mines or natural gas plants, nuclear plants, whatever you want. And this tool would extract the right data from the GIS based upon your location, feed it into a text file, and run GeoPhires. And from that, then we get lots and lots of information about each one of those locations, which we could then use to rank those locations, you know, based upon LCOE or carbon reduction, or, you know, whatever it is you want, then to rank those and prioritize those points as which ones seem to be best. And then you need to go in and do the details, but this would be kind of a ranking tool.
Very nice. So it's going to do a lot more than just geothermal.
Yeah. Okay.
Looks like
pass it back to you, Jackson.
Yeah. Well, great. Thank you, Dr. Ross. It was very interesting. So on to our last presentation of the day, but certainly not least, we have our friend, Dr. Mohammed Khalid. He is an expert in directional drilling and drilling in general. Some of his previous work developed lightweight deployable rigs, which I think are going to be crucial for accessing geothermal in some of the more remote regions of the world. And besides Mohammed's work on machine learning that he's going to talk with us about today, Mohammed is also collaborating with Project Interspace on a heat flow database project, as well as investigating the potential for repurposing hydrocarbon wells for geothermal production. So if anyone thought of some more questions on that, I know Dr. Khalid would be more than happy to discuss that as well. So please go ahead.
Yeah, sure. Thank you, Jackson. So can you see my screen? My sound is clear?
It's perfect.
Okay, awesome. So hello, everyone. It's a great pleasure to be with you today. So my name is Muhammad, and our today's talk will be about geothermal heat management and resources assessment. So let me go to the pointer. Okay, so basically our agenda for today, we are going to start first with the motivation. So what is the problem we are trying to solve today, and what is our proposed solution? Then we will jump directly to the two main ideas of today's presentation, which will be heat management in geothermal wells and heat flow mapping. Finally, will be a summary and publications that already published regarding those topics. So there are two basic questions we are trying to address in today's presentation. So the first one is how we can safely drill high temperature geothermal reservoirs, especially when the temperature exceeded 150 Celsius degree, and avoid unplanned trips due to downhole tool failure and bait dam. So for your information, most of the drilling downhole tools are rated to 150 Celsius degree. So if your plans that you want to drill beyond this temperature, which is favorable from the geothermal electricity generation, you should drill, in a way to protect your tools that are rated below this temperature. And I'm going to show you how we can do this. So our solution for the first question is we need what we call the better heat management while drilling. How we can do this? Basically by three main points. First, we need a numerical models that can accurately predict the downhole temperature. So we had at least a better prediction of what we are going to encounter while drilling this high temperature formation. What you are going to realize during the presentation is that it is a kind of a multi-objective problems where a lot of variables are going, to work against each other. And this is why, yes, you might have the results, but you might don't have, enough time to interpret everything. And this is why we propose here the idea of what we call the drilling heat maps, which is a kind of a user-friendly tools that we can use for well design and real-time decisions. Okay, so now we have the numerical models. We know an approach that can help us to interpret the results, but as everyone knows that numerical models are computationally expensive. So how we can simplify these models by using data-driven approach that we called machine learning models for giving us the same results by capturing the transient behavior of the downhole temperature. So this will be the main idea of today's presentation, and I will take most of the time. Of my presentation time. The second research question is how we can identify attractive area for geothermal developments. Especially in the US, we had hundreds of thousands of oil and gas wells. However, one of the biggest challenges we are facing is we don't know what is the uncertainty in this downhole temperature that we already measured before. And this is why we had a project that already Jackson related to with Project Inner Space is to assess the US heat flow database. And our ultimate goal will be generation of high resolution temperature maps. So let's now move to the first point of today's presentation, which will be heat management in geothermal wells. So a quick overview about the numerical models that we use. Basically, we use the Navier-Stokes equation for pipe flow. So we solve the continuity equation, momentum equation, and energy equation. And our ultimate goal is to estimate the downhole temperature. So we wrote a group of researchers wrote our codes, wrote the code in MATLAB, and basically, we are estimating the bottom hole circulating temperature. So here we can see a model validation. So you see the numerical model prediction in blue, and the orange line is representing, the Utah Forge real field data. And the y-axis is the measured depths, x-axis is the bottom hole circulating temperature. And you can see how the model is nicely captures the bottom hole circulating temperature at different measured depths. Also here we compare the model with a well-known analytical model called Hassan and Kabir. And you can see still that the mean absolute error is around 3.1%. So the first step was to validate the model just to be sure that our model's estimation is robust. Let's now go dive on some of the analysis that we conducted. And basically in this presentation, I'm going to focus on the Utah Forge field. So for those who are not familiar, Utah Forge field is one of the biggest geothermal fields here in the US. So this study is mainly focused on heat management in Utah Forge field. And what you can see here in the first start, in the first chart is on the left, that when you start pumping or drilling, you are pushing the fluid outside the wellbore, so the bottom hole circulating temperature is reduced until it reaches what we call the semi-steady state. However, when you stop circulation, and normally we stop circulation for multiple reasons, like for example, drilling mud pump failure, or for example, we need to take a connection, etc. You can see this kind of, again, temperature buildup in the downhole temperature in a logarithmic relationship. The chart to the right is basically showing to you the annular mud temperature at different time interval. So the blue line is while circulation, and once you stop circulation, the annular mud temperature started to shift toward to the in situ formation temperature. Why this chart is really important? First, because one of the misconceptions we had in geothermal field is while drilling, the maximum temperature will be at the bottom. This is correct if there is no circulation, But basically, while circulation, what this chart is telling us that the maximum temperature is 300 meters away from the bottom. Why? Because when the fluid exits the drill bit, you're still pushing the fluid. You are pushing the fluid away from the hot formation, and still there is a heat interaction. So the maximum temperature is reached not at the bottom, but 300 meters away from the bottom of the wellbore. This is really important because when you are using the downhole drilling tools, especially like an agitator or whatever, and you assume that away from the downhole, your temperature will be less, this will not be the case. So you have to watch out. Then we started, to study the impact of the drilling flow rate. And it makes sense when you are bumping the fluid at faster rate, as we can see, the downhole temperature are less. This is really expected because, you are reducing the residence time between the formation and the drilling fluid. But what was really interesting in this analysis, two main points. So the first one is the impact of the flow rate is not only during circulation. When you stop the pump, what we can see that the case that we use the higher flow rate, the downhole temperature, even when we close the pump, is still less than lower flow rate case. Why? Because basically this chart is telling us the near wall formation temperature. When you pump at higher flow rate, you cool the near wall formation temperature. And when you cool the near wall formation temperature and you stop circulation, the near wall formation temperature has a lower temperature. So the build-up in your temperature will be even less. Another interesting thing is, at constant mud inlet temperature. So basically on the drilling rigs, sometimes we use what we call the mud coolers. So the mud coolers' responsibility is to inject the fluid inside the flow rate at lower temperature. Again, the target is to reduce your bottom hole circulating temperature. And what we find really interesting is, beside, bumping is going to reduce your bottom hole circulating temperature in all cases, there is a kind of a fixed logarithmic relationship at constant mud inlet temperature. During the presentation, you will find me emphasize a lot on the concept of a simple mathematical relationship. It is really important for drilling engineers, especially who are working on geothermal drilling, to understand this kind of simple relationship. Because if you understand it, you don't need even to run, heavy computational numerical models. The second analysis was using what we call the mud cooler, injecting at lower mud inlet temperature. And of course, injecting at lower mud inlet temperature, you can see your bottom hole circulating temperature is reduced in all cases. And again, a linear relationship at constant flow rate is observed. It is another misconception was observed in a lot of webinars is, mud cooler will be helpful all the way. However, this drilling heat map is telling you, yes, mud cooler is going to reduce your downhole temperature, but up to a certain limit. So basically, the impact of the mud cooler degrade as your total wellbore measured depths, increase. So the impact will be less. And basically, this heat map is telling you the relation between, is telling you what is the bottom hole circulating temperature at different flow rate and mud inlet temperature. And one of the benefits of this kind of drilling heat maps as a powerful visualization tool is that it's telling you, what is your threshold. So for example, if you want to keep your bottom hole circulating temperature at 150 Celsius degree or below, you need to drill at flow rate, beyond 500 Celsius degree, beyond 500 gallon per minute. If you do this, you will be in the safe zone. However, if your flow rate go below this point, you are at risk of damaging your downhole tools. It is really nice to see the impact of these heat maps, in the well design. But this is not only, its own benefit, even while drilling operations. So if we had a case where we are, drilling at an acceptable downhole temperature, 400 GPM, 40 Celsius degree mud inlet temperature, and for any reason, your mud inlet temperature start to increase due to, mud pump failures, mud cooler, failure, etc. These heat maps can tell you instantaneously what will be your what will be your bottom hole circulating temperature. And this is really important because during drilling, you don't have time to wait for another numerical model to be conducted. But also, interestingly, it can tell you what is the remediation action you can take. So, for example, in this case, this map is telling you, again, going to 500 GBM can accommodate the increase in your mud inlet temperature. Our next analysis is understanding the impact of geothermal gradients. So, drilling geothermal wells and targeting the same formation temperature does not mean that you will have the same bottom hole circulating temperature. And to show this, actually, I'm plotting again another drilling heat maps, which showing the relation between the geothermal gradient and reservoir downhole temperature for predicting the bottom hole circulating temperature. And if we are targeting a geothermal reservoir with an in situ formation temperature to 150 Celsius degree, however, the geothermal gradient in this field are different. For example, like 24 Celsius per kilometer or 70 Celsius per kilometer as the forge field. Keep in your mind your bottom hole circulating temperature will be different, although you are targeting the same reservoir temperature. So in the 24 Celsius kilometer case, your bottom hole circulating temperature is 209. However, for the forge case, it's only 136. Why? Because basically, when you have a lower geothermal gradient, you have to drill more. So you are going to contact the high temperature formation more, and there will be more residence time between the drilling fluid and formation. This is why your bottom hole circulating temperature increase. In this analysis, we try to show the impacts of the drilling fluid physical properties, especially the fluid viscosity and different types of fluids. And what we find that increasing the fluid viscosity is going to reduce your bottom hole circulating temperature while circulation, even when you stop circulation. Because basically, when you increase your fluid viscosity, you are increasing the fluid convection resistance for the heat transfer. And you are like the fluids start to act as an insulation for the downhole temperature. So your bottom hole circulating temperature will increase, will reduce. Regarding what type of fluid, so in drilling, basically we use water-based mud, or we can use an oil synthetic-based mud. And it's really important to understand that water-based mud for drilling geothermal well is your best coolant. Why? Because basically water-based mud has a high specific heat capacity. So the specific heat capacity is the amount of heat required to raise the temperature of the fluid by 1 Celsius degree. Why this analysis is important? Because in the future, as we are speaking about deep closed loop geothermal systems, where we are going to drill long laterals, 5 kilometer plus, drilling long laterals, you will have a lot of drilling problems like hole cleaning issues, high friction, torque and drag issues. So most of the time, sometimes we need to switch to an oil-based mud. So this study is telling you, watch out. If you decided to switch from water-based mud to an oil-based mud, keep in your mind that your bottom hole circulating temperature is going to increase. Like our before last analysis will be the impact of the wellbore size. And basically, I'm showing here the relation of the hydraulic diameter. So the hydraulic diameter is simply the hole size minus the outside diameter of the drill pipe. And basically, increasing your hydraulic diameter is going to reduce your bottom hole circulating temperature or downhole temperature when you stop circulation. Why? Because you are filling the annulus with more fluid, so there will be more resistant to the heat transfer. Finally, one of the things that now a lot of people are speaking about is the idea of pipe insulation. And pipe insulation, I do believe it is the future for drilling high geothermal wells. And I'm going to show in a minute why. First, I'm going to introduce an idea which was proposed by the Department of Energy here in the US in 2006, which is basically welding, a 3.5-inch tube inside the 5-inch pipe and filling the gap between them with an insulating material. And this is dramatically reduced the pipe insulation from 45 watt per meter Kelvin to 3.12. And basically, you can see here in this chart how the impact of pipe insulation is really important, how it reduces the bottom hole circulating temperature, 41% in vertical wells, up to 16% in long laterals. Why is this analysis important? Because if you see here, beyond 1 kilometer, your bottom hole circulating temperature, especially at the forge, already exceeded the 150 Celsius. So your conventional downhole tools will not survive in this environment. However, if you use a pipe insulation, basically you can drill up to 4 kilometers safely without any problems. So insulated drill pipe is very important for the future of geothermal drilling. Okay, so now we already spoke about geothermal, numerical models for predicting the downhole temperature and drilling heat maps. But still, if you are looking for real-time decisions, numerical models will not help us because it is computationally expensive. And this is why we come up with the idea is to predict a machine learning models that can capture the transient behavior of the bottom hole circulating temperature in real time. So the machine learning model here is not going to predict the downhole temperature in a steady state, but we want it to capture in a transient behavior. So we started with the well-known supervised machine learning model, like deep neural networks, supporting vector regressors, random forest, extreme gradient boosting, etc. And we use the data generated from our numerical model, which is around 400 simulations, to train and test these machine learning models. And after training and testing these machine learning models, we start to validate the models against unseen data. And basically, what you can see in this chart here is the circulation time in minutes, and on the x-axis, and the y-axis is showing the bottom hole circulating temperature in degrees Celsius. And each chart is showing you the prediction of one type of machine learning model. So, for example, this is the deep neural networks. Here is the support vector machines. Here is the random forest. Here is the extreme gradient boosting, and here is stacked model. And stacked model is basically you are going to stack multiple machine learning models together, to get the better estimation. Basically, we can see that extreme gradient boosting in both case scenarios are capturing the transient behavior nicely. It's exactly matching, the bottom hole circulating temperature prediction of the numerical model. So the numerical model is the blue line. The colored line represents a different machine learning model. However, keep in your mind that in this analysis, we assumed constant drilling parameter, okay? So this is why we started to second validation. And in this validation, we changed the drilling parameter in the same run. And here's like 4 cases of validation. So still the XGB boost can do well in capturing, the downhole temperature with a mean absolute error below 5 Celsius degree. However, we can see how there is a high residual error, especially when the drilling parameter change. So when the drilling parameter change, there is a high residual error, then these errors decrease with time. And of course, this result was not satisfying to us. This is why we shifted to what we called time series machine learning models. So keep in your mind, when we speak about supervised machine learning models, these models deal with each row as an independent data point. However, this time series machine learning model had what we called a memory. So it takes the previous steps as an input in the next step. And this is why these types of machine learning model is very powerful, especially when you deal with the time series data. So I know someone might ask why you did not start with LSTM from the beginning, why you have to go with supervised machine learning model, for a couple of reasons. First, supervised machine learning model is easy for interpretation, can be easily trained and tuned, and even it's computationally easier. So LSTM, I would say, is much difficult, and this is why we started with the supervised machine learning models. Here you can see, for the static condition, when we did not change the drilling parameter, how the long short-term memory model, which is a special type of recurrent neural network, can capture the transient behavior. When we do the second validation, and if you remember, this was the results of the XGB boost, the LSTM do a perfect job in capturing the transient behavior, even when there is a change, in the drilling parameter. So the mean absolute error from the maximum mean absolute error reported from different cases was below 100, was below 1.5, which is really good result and telling us that the developed model can be a good alternative, for the heavy computational numerical model. Okay, now we finish the drilling part. And going to the heat flow mapping or, the geology. So what is the relation between, these two topics? I'm going to show you basically like 2 slides, because this is a current work about what we are doing now. And of course, feel free to ask more questions. So the main problem that we had, in the US database is there is high uncertainty, and there is a lot of missing information in the heat flow, how the heat flow value is calculated, what is the correct, how the temperature was corrected, and even the rock thermal conductivity. And this is a big topic because especially for rock thermal conductivity, people made a lot of assumptions that most of the time it is incorrect. So how this is going to impact the drilling and other stuff? First, you need a reliable heat flow data, temperature heat flow data, because you need to make a fair assessment of the geothermal resources. If you don't know how much uncertainty in the data, you cannot build your business models, and you cannot take a decision to invest in geothermal. So it's really important to have this understanding. Also, it is going to impact your downhole temperature prediction. In all the previous slides, I assume we used, temperature gradient and rock thermal conductivity as a major input in our models. So if this data is incorrect, or we don't understand how much uncertainty on it, it's going to impact our prediction, even on the surface facility design. Because your nightmare in geothermal is to design a surface facility for 5 megawatt, and it ends up only generating 2 megawatts. So you basically consume your money. So what we are doing now, we had a worldwide collaboration with Project Inner Space and the International Heat Flow Commission for basically evaluating the US heat flow database. So we are investigating it first by compiling and review heat flow, temperature gradient, and rock thermal conductivity from different sources. So we are combining all the heat flow database that we had here in the US and put it in a standard format. And our ultimate objective will be to reveal the missing information or any insufficient documentation. Why is this important? Because when you put all these database together in a standard metadata format, it will help you for reliable geothermal exploration and also for digitization. Because if you are a data scientist, you need to deal with a structured data. If you are going to deal with unstructured data, you will spend tons of time and effort to put everything together. So one of the outcome of this project is to standardize the data in one format to help the company, moving to the digitization. So what we are doing now is basically aligning the US heat flow database with the International Heat Flow Commission standards. And why we are doing this approach? Basically, because the International Heat Flow Commission standards, its final product is, beside providing you the data in a structured meta format, you will have a combined quality score. And the importance of this combined quality scores is going to tell you, what is the heat flow uncertainty? What is the inherent accuracy of the temperature gradient and thermal conductivity determination? What is the perturbation effect? And what I mean by perturbation effect is, what is the impact of erosion on your temperature estimation? What's the impact of sedimentation, etc.? So it is really important for the decision maker to have this knowledge before building their business model to invest in geothermal wells. So in summary, what I have shown you so far is how a numerical model was used to show the impact of various cooling strategy on the downhole temperature of geothermal wells. Also, I showed to you two examples how drilling heat maps are quick and powerful visualization tools for optimization geothermal drilling during the well planning phase and real-time drilling operations. Also, how a novel long short-term memory machine learning model was developed to precisely simulate the transient behavior of the bottom hole circulating temperature in geothermal wells. And finally, our current or ongoing work, which is evaluating the US heat flow database and generating high resolution temperature map, are really vital for commercial energy production from geothermal resources. So like since I guess 2021, 2022, a lot of publication goes out. So like what I have presented so far is published or will be published within 1 month or two. So it is a big topic. I know I was moving very fast, but I tried to be concise. So if you are interested in one of these topics, you will find a dedicated publication in a Q1 journals or in a or in a prestigious conference. So with that, again, I'm really happy to be with you today, and please feel free to ask any question, and I'm going to hand it over to you again, Jackson. Thank you.
Thank you, Mohammed. Very interesting. And maybe while people are thinking about some questions there, I wanted to ask you, in the drilling study, were there any big surprises that you got out of your findings, or something that was unexpected that really excited you about the research?
Yeah, I would say one of the most things that you will find people always surprised is the idea is, where is your maximum downhole temperature will be? Mm-hmm. Because all the people think by default, your maximum downhole temperature is at the bottom. Mm-hmm. But, if you remember, I showed in the slide, while drilling, you are pushing the high temperature fluid from the bottom a little bit up, away from the bed. So one of the surprise was that the maximum downhole temperature while drilling is 300 meters away from the bottom. I guess this was really interesting finding. The second thing is, and we had a dedicated publication for, is people deal with geothermal heat management as only one case. So for example, when they spoke about the impact of fluid properties or pipe insulation or whatever, they deal it like all the cases are similar, but this is incorrect. You have to differentiate between drilling high geothermal gradient wells like the Forge field, or if you are going to drill a geothermal well in Texas, which has the average global geothermal gradient, 35 thesis per kilometer. The heat management techniques will be completely different, because your bottom hole circulating temperature is different, even if you are targeting the same reservoir temperature. So there was a couple, interesting things, honestly. But this is like two things I always like to speak with the people because it's surprising.
Great. Thank you. Well, it doesn't look like we have any questions from the audience here. So thank you, Mohammed. I appreciate you taking the time to talk with us today. And thank you for everyone for joining us for the Texas session of Geotheroom. So we'll see you all next month. Yes.
Thank you. Have a good day.
Thank you.
Bye-bye.
Bye, Malcolm.